Hello linear algebra students. This video should help with several issues that some of you are having with the amount of work to do. This should help. All right, so you of course have solved systems of linear equations in previous classes, possibly in pre-calc, or if you took a 1324 business math type class. And these, what I have here today are three examples, very simple examples, just two equations and two unknowns, but they illustrate a number of issues, okay? First of all, when we say solve a system of equations, that means we want to find replacements for the variables that satisfy all the equations equally well, or we say simultaneously. So solution sets, it turns out, have either no solutions, one solution, or infinitely many. And why that's going to be true, why that is true, is you're going to understand that in a few lessons. You'll be able to prove why that is. So I've chosen three examples of just two equations and two unknowns to illustrate those different type of solution sets, at the same time as trying to show you what we mean by solving these by hand, using algebra by hand, using techniques like elimination or Gaussian elimination, or using a computer program like that in a TI calculator that does it for you. Now I've already does the Gaussian elimination for you, but that doesn't mean it solves everything. So I've already done a video where I explain why a Gaussian elimination in the form of rref and ref on your TI calculator, why they work, okay, mathematically. And you'll understand that video better as we go along the semester as well. But let's just talk about some examples. All right, so example one. We want to solve 3x minus 5y equals to 20 and 3x minus 5y equal to 30. Now the solution set to this would have to be all those vectors in R2 with coordinates x and y, whose x and y coordinates satisfy both of those equations. Now, as a human being, you're looking at that and saying, oh, how is that possible? At one point, you want this expression, this linear combination of x's and y's, to be equal to 20, and at another point, you want it to equal to 30. That's impossible. Well, it's true. We're going to find out that this solution set is empty, okay? But algebraically, how does the algebra realize that that's a problem? Okay, so if we are using the methods that you've been taught up to this point, say elimination or substitution, you might rewrite that equation in the slope-intercept form, and you rewrite the other equation in slope-intercept form. And notice by the slope-intercept form, that's easy to graph and see that these two lines are parallel. Notice that their slopes, M1 and M2, are equal, okay? Parallel lines, the definition of parallel is that the lines never intersect. Or if you want to put it this way, what is the point that's in both L1 and L2? There is none. It's an empty set. So what are the set of XY pairs, or written this way as a vector in R2 with coordinates XY, that have x's and y's that satisfy both equations? What are the set of vectors? Nothing, no vectors. This is an empty set. So we say, let's see, can you guys see all this down here? Not quite, sorry. So let me just caution you, something that comes up quite a bit. I gotta make sure that everybody's aware that when we, well, actually Drew might help me there. When we say there are no solutions, that we're saying there are zero solutions in S. Some people fixate on the number 0 as if just writing the solution set is equal to a set with a 0 in it is the same thing. No, the empty set is not the same thing as a set containing a number, okay? So we're just writing the solution set is equal to 0. No. There's nothing in that solution set, okay? No vectors in R2 with coordinates x and y satisfy both equations. All right, so that's the easiest type of situation to solve. You realize there's a contradiction, and you go, oh, the solution set is empty. Okay. Next easiest is if you have a system like this, 3x minus 5y equal to 20, that's the same. And now over here we have 6x minus 10y equal to 40. Okay, so they're not as close looking, but if you actually put the first one into slope-intercept form, it's still 3/5 x minus 4. And if you do the same thing with the other one, oh, you realize that is exactly the same. So in this case, you'll notice that both y1 and y2, the first line and the second line, their slopes, m1 and m2, are exactly equal, like it was over here. But here in addition, we also have that their y-intercepts are the same. Their y-intercepts are both 0, -4. So that's the distinction in terms of slopes and intercepts between these two cases. Right over here, you'll notice that B1 and B2 were not equal. Right here. B1 was not equal to B2. But if both the slopes and the y-intercepts were equal, oh, that's exactly the same line. Or people will say the lines are coincident. All right? Now, but what goes into the solution set? What are the set of x, y coordinates that satisfy both of those equations? Well, the set of x, y, here we're writing it as a vector, such that this equation is true. Or you could have put in this equation, or you could have put in that equation, because they're all equivalent to each other. They are representing that there is a whole line of points that whose coordinates satisfy the criterion. Or there's a whole line of the heads of points that are the heads of vectors that satisfy this equation, this system. So there are infinitely many solutions in that solution set. So we just went from no solutions whatsoever to infinitely many solutions. And students seem to have a hard time with, once they realize they're in this sort of situation, how to write the solution set. Well, this is an example. Question for you. Is either this solution set or that solution set a subspace of R2? You should stop the video and think about that. That would be a great test question, by the way. Assuming you would not have thought about that, the answer, of course, is no. Neither of them have the 0 vector in it, do they? So they can't be subspaces. Okay. Example 3. Let's see. Excuse me. That's making you dizzy. And are we seeing, this is example 3, and there's a nice glare right in front of that. And that's just going to put that glare over here, so we need to bring you over here. Somehow. Okay, sorry, I guess I'm going to put you back here. And then I'll have to move you again for the 4th panel. All right, so now we're looking at example 3. Okay. 3x minus 5y equal to 20 again in this example. Now we have 3x, almost the same line, except now I've changed one of these coordinates over here. I've changed the y coordinate. Well, you solve for y in each of those to sort of see what's happening geometrically. Oh dear. Sorry. You're looking at two different slopes. So now M1 and M2 are not equal. So that means these lines are not parallel. What we say instead of, if lines are not parallel, they are transverse. Notice that that does not imply that they're at right angles, okay? In other words, there's some point where these two lines intersect. The coordinates of that point, A, B, are going to give us the coordinates of this point. Let's see if I can get this. Yeah. The coordinates of that point A, B are going to give us the coordinates of that vector that solve this system of equations. Right? So we need to find this vector whose head is at that point. Okay? That's what's going to go in here. Well, that requires more algebraic work. We call this a 2x2 system. That's fairly minor, okay? But we want to be able to, in this course, deal with systems of tens, millions, hundreds, or just generic, m by n, m equations with n unknowns. So I'm just using this simple example to talk to you about how the solution is found. Okay. All right, so to solve for this A and B, I start with some sort of notation you probably used in a previous course, or thinking about how you're going to take this system and do elimination on it, right? You can see there's that 3x there and 3x there. If you could just do something. Now there's all kinds of casual things that people will say here, but there are actually only 3 legitimate types of operations on a system of equations. You'll notice that I have taken these numbers, 3 minus 5, 20, 3 minus 4, 20, and just lifted them out of that system and put them into an array. Because when we do those algebraic tricks here, we're really just working with the numbers. The x and the y and the equals, we don't need to keep rewriting that. We've got a lot of busy work to do if we're doing this by hand. So let's just take the numbers off here and call, instead of that's the first equation, that's the first row. Second equation is represented by this row. The process of stripping off those numbers and plunking them in here is easy for students. It's the process later of reversing that, slapping those numbers onto an equation or onto equations. That seems to be where students have a difficulty. But just remember, it's just as easy as this process of stripping these off and plunking them into that array. Okay, so turns out that there are three equivalent row operations. In other words, this array will represent a system whose solution set will be the same as this one, will be the same as this one, will be the same as that one. That other video I made that talked about why Gaussian elimination works was proving that to you, okay? So let's look at this example of actually using those row operations as needed. Now remember, your human brain is much smarter than the calculator, which has been programmed to handle many different possible cases. You want to just eliminate that 3 there, right? So what you're tempted to do is to, well, this is how to phrase it as an equivalent row operation. You want to replace row 2, the old row 2, with the new row 2 that's equal to the old one plus -1 times the first one. Now I'm showing you some tips for getting through this process when you're doing it by hand or when you have to show the row operations. And that's also, you're tested on knowing the what would be the appropriate row operation. So let's say if you want to eliminate that 3, you're just going for that, not thinking about the Gaussian elimination as written up in computer programs, but just let's get rid of that, make that into a 0, okay? So if you have this part here that you're going to add -1 times row 1 to this row 2, I suggest, if you're doing it by hand, you actually write down, I'm taking -1 times row 1, there's row 1, I'm multiplying by -1, here are the numbers. Why did I do that? Because it made it really easy to add these and get the correct numbers here without making a mistake. Okay. So there's my new row 2. Okay. As a human, you go, oh, I've eliminated a lot of stuff. Let me go back to the system of equations and just say, look what I've got. So this process of going from the array back to the system of equations, you have to be good at this, get good at this. So what does this array mean? This augmented matrix, sorry, these things are called augmented matrices. 3x minus 5y is equal to 20, is the first line still, I haven't touched that. The bottom line becomes this equation. 0 times x plus 1 times y is equal to 0. What's all that mean? Well, that just goes away and we're just left with y has to be equal to 0. Oh, great, we've got one of our coordinates. And then, of course, we would just substitute that back in here, this y equal to 0 in here, and say, okay, 3x is equal to 20. All right, so x is equal to 20/3. Okay, so that's the human path tries to do the least amount of work, right? That worked here well, but does that path work for all possible instances? And the answer has been found to be no. So a process called Gaussian elimination, instead of just breaking right over to here and getting a solution as soon as possible, would have kept working with this augmented matrix until it looks something like this. Where's my glare? Is that giving me a problem? Hopefully that's better. Okay. All right, so one row operation, and as a human, we're like, okay, we're out, we've got our solution. But in general, that might not be the best path to take. So we've written computer code that take these systems, these array of numbers, and try to provide programs like rref, which stands for row echelon form, or rref, reduced row echelon form, that take all the grunge work away from the humans and just present the answers, right? All right, so the computer program wouldn't have done that. They would have first actually made this first number appear into a 1. To do that, they would replace the row 1 with itself multiplied by 1/3. So that actually, under the method Gaussian elimination, that would have been the first step. The good news is these steps are interchangeable, okay, if using these row equivalent operations. It doesn't matter what order we do them in. So we'll do that now, and so we're looking at something like this. Oh, well, this form right here, that's what we call row echelon form, where we have leading 1 and just zeros in the column apart from that. And the echelon here, this one is a leading 1. Row echelon form doesn't care that that's not a 0, okay? If we go one more step, we're going to see not only this row echelon form, but it's reduced, okay? So that these 1s have, in their columns, there's nothing else but zeros, if possible. Okay, so this one is called reduced row echelon form, and if you have the TI calculator, you can get to that program. Let's see, working on the glare for you on that screen. Okay, well, the buttons first of all. Second function matrix. You go across the top there, there's the option to do mathematical programs, and there's a list of them. You go down here a little bit, you'll first get to rref, which is nice. but actually we usually go all the way to rref. Okay, you press enter and it says you want to do Gaussian elimination into reduced row echelon form of what? You have to go back in here to matrix land and grab a matrix. You press enter and it gives you the row reduced echelon form. Now you'll notice here this has got a lot of decimals in it. To get rid of that, just go to math. Automatically it's set on frac, press enter, and you get it in fraction form, which is a lot easier to deal with and more exact. Okay. So if we had combined this row operation and that one, this would have put it into rref form. Okay, we could jump over at this point and do a system of equations. It would just say 0x plus 1y is equal to 0. Same as before, but it would also say x minus 5/3 y is equal to 20/3. But y is equal to 0, so. Okay, well, rref just kind of does that in a oneer. So let's concentrate on this form. So you'll notice that rref, in situations like this one where we're talking about the lines are actually going to produce a unique solution, you're going to see, this is called the identity matrix. It's the 2x2 one, right? 2 columns, 2 rows, 2 columns. And when you see the identity matrix there, then you can just read off these coordinates as your answer. Yes, what we had concluded before was correct. The solution set is one vector with coordinates 20/3 and 0. And don't worry if you see the identity here and there's a 0 over here. That just means that coordinates value is the number 0. That's okay. Now, what if we had tried rref? Oh, and by the way, now once we found the solution, you're probably thinking, well, wait a minute, that picture was really messed up. So let's go back and fix that picture. Yeah, because these guys should be intersecting on the x-axis, right? Now we know this coordinates of this point are 20/3 or 6 2/3, 0. If we can see, oh yeah, this was messed up. What, my drawing wasn't perfect? Oh, yeah. So 1, 2, 3, 4, 5, 6, and somewhere like there, that's where those two lines should have been intersecting. Should have looked more like this. So if that's been bugging you for a while, now think of it as fixed, okay? All right, and so the solution written as a vector would have the 20/3 or 6 2/3 here, 0 there. Can you guys see that? So that's the solution set gets written as a vector. Is that a vector space? A set that contains that one vector? No, it's not. It's not a subspace, but it still is a solution set, okay? It doesn't contain the 0 vector, so it's not a subspace. All right. What if we had tried, back to this other topic, what if we, in example 1, what if we had tried using rref right from the beginning, right? So if we had, example 1 had 3x minus 5y equal to 20, 3x minus 5y equal to 30. If I'd made an augmented matrix like that in the calculator, in matrix land, and ran rref on it, it would have given me this answer, which says, what does that say? Oh, and by the way, here's the row operations that would have got us there. If you were doing it by hand in example 1, you would have, let's see, replaced, you would have gotten rid of this 3 by adding to row 2, -1 times row 1. And rref is going all the way to this. They don't have a 10 here. They would have done one more. So how would they get the 10 reduced to a 1? Well, they would have replaced row 2 with 1/10 of itself, right? Scalar multiple of itself. So they're looking at this. What does that mean? Okay, so can you unwrap an rref form correctly? That's a skill you need to develop. Okay. All right, so this augmented matrix becomes this system. All right, just slapping all those coefficients onto the right places at first. Be able to do that. Students resist doing that for some reason, I don't know. A lot of students will see something like this and go, I don't know what's happening, and run away, okay? Just lay those numbers on as coefficients on the system again. Be able to see here, yes, okay. What does that mean? Well, the top means what was fine, first equation, but this one is saying 0 plus 0 is equal to 1. That's a contradiction. So the algebra, this algebraic calculating machine, can't say to you, blink, 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 solution set is empty. It just gives you a contradiction and expects you to logically infer that therefore this system never had a solution. If a series of legitimate algebraic maneuvers results in a contradiction, that means this system is inconsistent, and because these were row equivalent operations, that means this system, the original system, was inconsistent, had no solution. Okay? It's easy if you just will take these numbers and put them down on in front of the variables and look at what you've got. What happened in example 2? If we had used rref. Example 2, you would have had, in here would have been a 6, a minus 10, and a 40. And you remember that this is just double that, right? So in example 2, if they had added -2 times this row to that one, they would have got a 0 here. Sorry, let me block that. I would have had a 0 there. Can you see that? Right? Because -2 times row 1 added to row 2 gives you a new row 2, all zeros across. What does that mean? It would have been different, possible different operations there. I'm going to emphasize going from the last augmented matrix, the rref, in reduced row echelon form into a system of equations. The only difference would be this. The only difference is that you would be looking at 0x plus 0y is equal to 0. Is that a contradiction? What does this imply? 0 is equal to 0. That's not a contradiction. So what else is left here? Let's see. X minus 5/3 y is equal to 0. There's no contradiction here. It's just saying if you find the set of all xy such that, well, let's see, a way we could write it is that x is equal to 5/3 of y, well, then you have the solution set for the first system. Right? This implies that. There's no contradiction. That's just superfluous information. Yes, yes, we know 0 is equal to 0. No contradiction. What's left? This statement here. And if you remember, that's a whole line. Sorry, in example, in example 2. That's when the two lines are one on top of the other, coincident. This is another way of describing an infinite set of vectors whose first coordinate is 5/3 times the second one. Okay? Infinitely many solutions. So your task is to get used to taking the result of a reduced row echelon form, putting it back into the system and correctly interpreting that. That's something that takes a while.